Welcome to today's webinar with the title Design for Manufacturing or Design for Sustainability. I am Andreas Schilp, your host of today's Wirt Electronic Circuit Board Technology webinar, and I would like to welcome you. The speaker in today's webinar is our qualified specialist Andreas Dreher from our Technical Project Management. Welcome back, Andreas. And now I wish you lots of fun and new information.
Thank you for your kind introduction and also welcome from my side. We will look today on the sustainability of PCB production, and we will focus on different topics like the basics before a design creation, the factors influencing the PCB production from the design perspective, how you can improve the design for being more sustainable. And we will also show you a development of new processes like the additive solder mask via inkjet. You find the contact details for further questions here on this slide if you want to have some direct conversation. Before we jump into the details of sustainable PCB production, we have to define the word sustainability because there are a lot of different views to it, and the Wirt Electronic created a very informative paper about it to define the topics in several categories like products and services, resources in the production and their influence to the environment, and also, last but not least, people and society. And you can also find on this homepage an already done webinar from our CEO Daniel Klein, who is talking about the company politics about sustainability and creating a better tomorrow together. So let's focus in this presentation on your products and our resources and the influence to the environment. And when you start a very new design on a white paper and think about the features which this new setup, this new product should fulfill, very often you start by defining the components. And with defining the components, there's really like a gear train. If you set up here this parameter, all the gears in the system will move and will influence each other. So if you have very early designs, the definitions like the shape and the size of a PCB, this will influence a lot of other factors also. For example, a round PCB takes more place in our production panel than a square one. Or the material, why has a PCB always to have a thickness of 1.6 millimeters? Could it be thinner? If you use just 1 millimeter of thickness, it's 0.6 millimeters less material, and less material means less resources and more sustainability. Also, when you think about the connection of your board to the outside world, do you have a component connector? Do you have to solder them in? Can it replace by a flexible PCB where you don't need the cables in between? Can use an edge connector? Typically they are with galvanic gold. Can it be replaced by a printed polymer surface without a galvanic process? Also the requirements, if you have pretty high requirements, we need maybe some extra processes, which we have later look in the presentation, which will directly influence sustainability and also the effort in the PCB production. So all of these topics are linked to each other, and that's why it's important to have a discussion and share some ideas very early on. Let's have a look on some deep dive like in the base material section. When you create a new PCB specification, you have a lot of options to choose. And if, for example, you use base material with a brominated flame retardant, we are locked to this. There are, in the meantime, in the last 20 years, it was a very huge development in a lot of new alternatives with halogen-free materials, where you don't use this bromide, which is here in his elementary form. It creates this typical orange dust and is used as a flame retardant and can be replaced nowadays with halogen-free materials. Or another example, if you have a high-speed board with several gigahertz area, often the layouts are on a PTFE-based material. Again, in the last years, a lot of new materials were developed where they avoided the use of PTFE, so Teflon in a product name. And if your specification is linked to the PTFE, we have no choice and to have to use it. Maybe if you, in a very early discussion, use other materials, we can change it here. A very practical example is often the definition of a glass transition temperature, the TG value, which is a good indicator of materials' thermal properties, how much heat they can sustain. And for example, in the specification, if you specify higher than 150 degrees and the datasheet of a material has, for example, a value TG 150 plus minus 5, by this specification we are not allowed to use this material, because if you have minus 5 degrees, it's not fulfills the specification. Is this really the intention of this labeling, or is the intention to use 150 material? So a better definition is very important. In that result, we have to use a TG100 material, which is higher cost. There is more effort in the production of the raw material, and also in the PCB production itself needs higher process temperatures, which is a higher resource impact. So if this foundation in the PCB specification is already wrong, and we want to build a house on this foundation, the foundation is pretty weak, it's not sustainable, and this is a very important impact very early on before we ever produced a board. So PCB specification is here a very important point very early in the project. Also, of course, the PCB size itself has a major influence. So if you have a big board, you need more material, more space, more resources. If you can make it smaller, save some space, of course the boards get typically cheaper, but also needs less resources and is more sustainable. Very often the PCB size is given with the housing. So sometimes you are not directly can influence the size, but what a very good point is, how is the panel in our production? We have pretty big production panels. How occupied is it with PCBs? Can you put, for example, 3 boards or 4 boards on a panel which has 1/4 of a resource saving here, and also, of course, in costs. So my colleague Jürgen Wolf made also already a webinar to this topic. It's I think 1 hour and 20 minutes, so I cannot put all these features in, but it directly influences, of course, the cost itself, but also the resources and so the sustainability of a production. You can find a link here to get further details about this topic. So if we sum up the specification, it's very important to have a specification as generic as possible and as precise as necessary. And for the base material, it makes really sense to use these definitions in the IPC 4101, where they have this famous slash sheets for the different material classes. Typical classes is /21 for TG135, in that case still bromided. TG150, TG170 with the classes, for example, in a halogen-free manner. Also, a very important point is sometimes it is possible to use equivalent base material to reduce special transport. If we have a material not on stock, but a comparable material, if we have to buy the special material and we have to do, for example, bring it in by plane, this will influence the environment also. So if we can use an existing material with an equivalent base material, here special transports can be reduced. To fit in the PCB size in the panel is very important, and sometimes here we are talking really about a few millimeters. Sometimes 1 or 2 millimeters can make a very big impact, so this should be always checked before you order large quantity of PCBs. And regarding the design parameters, we have in the following slides a lot of inputs which give you an idea about the impacts. So let's jump in our production. When you have done all this specification and you order the PCB, we start with the inner layers, and you can see here a typical machine in our facility in Niedenhall. Very often the boards are produced in such horizontal lines. The boards itself are transported on all these rollers here, which fits through the whole machine. You can see here the green parts here are a lot of pumps which are pumping all the chemicals, the process chemicals in the bath. And here you see a module with a spraying nozzle where, for example, the etchant solution is put to the board and the pattern is etched. When we look on a schematic how this is produced, we get the base material with 100% copper, and we do a subtractive process. We remove the copper where it's not necessary. So we apply an etching resist, put light on it, develop it so that we have some free space. In this space we take the etching medium and spray it in so that the etching is slowly going into the deep, and as deeper it gets, as more the sides also get etched. So here for every micron you etch into the depth, also the sides are etched away. We know this in beforehand, so that's why the etching resist is always bigger. If you order, for example, an 100 micron track, etching resist can be, for example, 120 micron, so that this etching loss is compensated. But for this compensation, we need here some space. So for us, this space in between is very, very important, more important than the track width itself. And after etching, you see this typical trapezoidal shape of a track in a cross section. So, and of course, as I mentioned, it's deeper you have to etch, as more you need to the sides. So in the IPC, you can order different foil thicknesses with, after the IPC specification, some minimum values. And for us, very important is this spacing. So as bigger the copper gets, as more spacing we need in between for the inner layers, for the outer layers, different line width. And here you can help us to make the board more sustainable if you give us a little bit more space. Let's have a look on a practical layout example. So on the left-hand side, you have a BGA pattern with a pretty tight space, and there you have not a lot of space. So the area here, the space is pretty small. But outside the component, where you have a lot of space, you can add big spacings, wide openings to improve the yield and so make the production more sustainable. So in narrow spaces, it has to be small, but outside the narrow spaces, you can implement generous spacing that we have a little room to work here. Also, a good thing is to add teardrops. Teardrops is this conical shape on the connection to a track that if we have here in this sketch a via, afterwards if the via has some tolerance and it moves a little bit to the side, if you add the teardrops, the IPC allows a bigger tolerance and makes the production more easy. Maybe you can even improve the drill tool, use a bigger drill tool, which is a big influence in wear out, for example. Makes the board more reliable, makes the tolerance space bigger, makes everything more sustainable. Also, for us, the space is more important. So if you have a standard line, it makes sense instead of using a symmetrical definition like 100 line and 100 space. You can, for example, implement a 80 micron line width and 120 micron spacing, which again improves the yield and makes the board more sustainable and also save some cost. If we go really deep into the machine, in the meantime, more or less all processes are digitalized. A few years ago, we used films, black and white films, which you put on the board and used a strong flashlight to make the development of the structures. In the meantime, you use either LDI, laser direct imaging, or direct imaging with some LED light sources, and you create a digital pattern on the surface. So the structures get digitalized. You create some pixels. A pixel can have a size, for example, on one machine it's 8 micron. And if you have here this rounding, where you want to create here a space around this pad, for example with 75 micron, with these pixels there can be local hotspots, small spots where the size is smaller, which such things can happen. And if you look here on this layout, there is nothing around, so it is very easy possible to make this space bigger, to improve again the yield, make the process more efficient and the board more sustainable. So to sum up this section, if you have narrow spaces, you have to use small conductors, but outside use more space. You can use asymmetric layout definitions instead of 100, 80 to 120 is the same footprint, and you make us in the production the life much more easy. Use teardrops. It gets an extended tolerance range. We can use sometimes larger drill diameter, which means less tool wear and a higher packaging. And if you can use new data formats, this is a growing section which we have to talk more and more in the future. New data formats like the IPC 2581 or the Gerber X2 file. You can implement attributes to the pads so that you can label this is a BGA pad, this is a standard line, this is an impedance line, and we can, according to these attributes, make adjustments as necessary, make selective adaptation possible, which helps to make the board more sustainable. In the outer layers, we use a semi-additive process. So we start again with a pretty thin copper foil with 100% copper. Add again the blue laminate on top, which is our resist. We plate locally on the structures which you need in your design, the tracks, the pads, for example. And afterwards we strip away the resist, then we etch the copper in between, and then remove the tin, which is in that case our edge protection. And then you have the finished structures. The good thing is you only add copper where you need it. The disadvantage of this process, it is layout dependent. So if you have big and small copper areas, the copper disposition will be different. So you see a little bit a height difference here, which is influenced by the design. Let's have a look to the design impact. So this is a real life application. You have here a mixed layout, which is fine. 50 micron copper on the outer layer was planned, 50 was reached. The etching process was pretty good. Here, only a few millimeters away, you have these tracks which have no copper around. So all the galvanic plating was added to these lines, and in the same board we have 20 microns more on the surface. The etching was optimized to the 50 micron and was not enough here. So we have a short, board is a failure, and you have a low yield. What can you do against such a thing? Use homogeneous copper distribution in the layout. So this is a pretty poor example. We have critical structures, freestanding, no shielding around, which is very hard for us in the production. If you add some filling areas like this crosshatch pattern or a dot pattern, improves the layout. Our most wanted thing is just copper flooding the whole area on the inner layers, on the outer layers, which is for the production the most sustainable thing. It sounds a little bit not intentional, because if you have more copper, it saves resources, but it's true. You can avoid extra processes, additional processes with this copper flooding. So if you have more copper, it can even be more sustainable in this special application. So this will improve the yield. It can also reduce some extra processes. So as more homogeneous the layout is, as better it as will get. This is an example. If you want to use copper dots, this can be a design rule for it. It has to fit to the layout. If you have a full plain area, there should be more dots. If you have a light, dense signal layout, it can be less dots, but a generous recommendation could be such a feature. If we have a look into the vias, if we want to add copper to the vias, we have similar problems. You can see here a picture inside a module in the galvanic line. They are not spray nozzles used, it's more like a hot tub, a whirlpool. So you have some standing waves here where the board gets processed through, and you have to force the galvanic electrolyte into the vias. And there are a lot of factors influencing the copper deposition, especially the board thickness, the drill diameter, the electrical field lines by physics, and the process, how much copper we add here to the process. What does that mean in a real-life application? You will always have more copper on the entrance of a via than in the middle one. This example is maybe a little bit extreme, but it shows the effect pretty good. You can divide these numbers by half in your head, then you get the typical 20 micron copper in the middle of a hole and 25 microns, 27 microns maybe on the entrance. This is defined very often by this aspect ratio, so the ratio between the board thickness and the diameter of the drill tool, which is a very good recommendation, is 8:1. This is a very typical limit. If you make the board thicker, if you make the drill diameter smaller, you can get pretty much, pretty fast, pretty lot problems. We solve these problems with additional processes, with extra processes, which is more resources, less sustainable. Also, if you have big drill patterns, like a BGA area, as more drills you have, as more of this effect you will see. Also, you will have a so-called bath tube shape, so on the copper distribution on the surface will also be reduced. And a good idea is, for example, to allow less copper in the BGA area if this is applicable to your design. And outside of this area you can have, for example, 25, and inside this area only 20. This can reduce additional process costs. And talking about copper specification, we see in a lot of specification that sometimes the specification of IPC class 3, which includes a 25 micron copper limit in a via, with the specification of IPC class 3 production and quality control. The 25 micron is only one parameter of this. If you order IPC class 3 after, for example, IPC 6012, you will also add test coupons and a lot of tests into the production. And there are applications which is this is useful and necessary and helpful. If you have critical applications where life depends on it, this makes sense. But if you just want to have a reliable board without all these tests and you want to have 25 micron copper in the via, a good solution can be just define a copper requirement on the drawing without mentioning the IPC class 3, so that we not get mixed up with this specification. If we have to add these test coupons, we have to remove, as shown here, some PCBs, so the occupancy on the board is reduced. We have to add more resources, more boards to the production to fulfill your order, which is more resources, less sustainable. Same goes along with impedance testing. If you have an impedance controlled board, we have to add for the control these test coupons. And again, if you add these test coupons, we have sometimes to remove PCBs, adds more, we need more material, and this can be avoided if these tests are not necessary. Good practice is here in the first order to add the coupons to test and prove that the layout is correct and the calculation was correct. And for the series production, when nothing is changed, these coupons can be removed to save space and resources. So to sum up this area in the layout, the circuit board is massively affected by the copper distribution. As more even the copper distribution is, as better it is. Flooding with copper surfaces is preferred. It helps conserve resources, improves the yield. Again, requirements for quality control and tests, the specification as generic as possible, as precise as necessary. Sometimes, do a first inspection for the first lot, and maybe in the next lot it can be removed. Also avoid taking cross sections from good parts. You can make, for example, the dielectric spacing. You can also measure on electrical failed boards. We talked about test coupons, limit their use as much as possible, and you can request a soldering sample from an electrical test failure to set up your soldering process with a faulty board, that you don't have to use a good one. So a few additional points. Sometimes via filling is necessary to make, for example, the board vacuum tight, and the IPC is giving a lot of different specifications to it. And I want to have a look with you on the Type 5 and a Type 7 board. It's the so-called filled and capped via, where you fill the via with some resin and then for the Type 7 make a cap on it that is completely sealed, and you can put component on top. And this is an extract from our filling webinar 1.5 years ago. If you want to have a look, you will find it on our webinar database. So how is it produced? Of course, we have to drill the via. We go to the galvanic, make the metallization and top and into the via. Then we go in a via filling process where we have a vacuum chamber, suck out all the air, fill this extra resin into the via, cure it in an oven, and afterwards we have this residue on the surface and we have to send away the residues. And then the Type 5 via is done, and if you want to have a Type 7 via, we have to add an additional metallization to close the lid and make a cap. In this process, in this vacuum filling process, every hole is filled. every hole present. If you have through-hole components and you want to stick a component into the hole, it's not possible with both technologies. So what we have to do, we have to drill additional holes which are not filled afterwards, after the sanding, go back to the galvanic, put some copper here in the via, also on the surface. In this step the cat is created. So to make a type 7 via, we have to drill twice, we have to go to the galvanic twice and make this curing. It is sometimes necessary. There are designs which cannot work without that process, but if you can avoid it, maybe this can be an option. If you have only one component which such a technology is needed, really sometimes with some intelligent design it is possible to get rid of this filling. So if you have a via and pad combination, sometimes it is possible to move the pad outside so that the pad is free, or in such areas maybe you can put them around it, use some solder mask barrier that you don't have solder overflow, and can use it without type 7. And again, don't get me wrong here, there are a lot of applications where this type 7 is needed. It's a proven technology, we use it very often, but sometimes with intelligent design you can avoid it and save here a lot of resources and additional processes. So a big step in the sustainability is an additive inkjet soldering. As I explained already, we have sometimes subtractive processes, and the conventional solder mask is such a process. So in the conventional way, you apply solder mask to the board 100% of the surface, either by curtain coating, by spraying, or by screen printing. And afterwards, again, you develop the solder mask and remove the unnecessary areas to have the solder pads. So you add 100% and remove a lot of them again, which is not always a very sustainable process. In 2019, after some development before, we installed inkjet printers, pretty big ones, industrial printers. In 2020, we started a big series production in the automotive section, and in the meantime, we developed some nice ideas in 3D topologies on the boards, which I showed you on a few boards. So what do we do here? We use an inkjet printhead. We have on the one hand side the inkjet nozzle where the solder mask is applied, and behind it we have a UV light which is curing the resin that it's stopped flowing, and the solder mask stays where it has to be. And then the printhead is moving, and now with this inkjet technology, it's a digital process. So you can say, okay, I want here one thickness and here another thickness, and you can create a lot of new things which were before not possible. If you are used to our webinars and our homepage, we work a lot with this practical samples where you can show you this technology. Also for the S-mask, we have some sample here where we have areas, for example, where we printed once, twice, or 3 times to create different solder mask steps. You can print graphical elements like logos or 3D structures. Unfortunately, in the picture is a little bit lost, but even the leaves of this tree are in a 3D shape. And if you want to keep it more technical, we can now apply solder mask in areas where it was not easily possible before. This cross-section shows a track with 250 microns copper, and with conventional solder mask it was not possible to have a good edge coverage. Here with inkjet we applied a lot of more ink here in this area than on the board itself. So we have 15 micron in this area. The step is 250 micron. On here on the corner we have more than 25 micron to make here a very good insulation, which is in a conventional way not possible. What else is possible? why is a PCB today green? Because, as I mentioned, you cover everything with solder mask and remove only the things where you need. With inkjet, we can turn the idea around, just apply the solder mask where you need it. And that's what we have done here with this example of a DC-DC converter, where we only printed a small ring around the through holes, for example, to avoid the areas, and the white stuff is just bare FR4 material. One disadvantage of this example is that the copper plane areas are gets nickel gold. Nickel gold is more expensive than solder mask, so this is maybe not a good idea. So in this second revision, we printed the gold areas, but not so much gold is needed, and you have no solder mask in this area. And to show you such a thing in real life, you see here my background is such a board. In the future, we can really think about why a PCB is typically always green. In the future, with inkjet printing, this should not be the case anymore. So to sum up, the S-mask additive solder mask, it's a fully qualified process. We have it in 2 production plants in Germany. We have ongoing production in automotive area, aviation area, and medical applications, which, as you know, are not the easiest areas, but it works here very good. It has a lot of advantages in this area. If you want, you can change your board tomorrow, either by a one-to-one conversion. So you send us just your Gerber files, as you know, and we can create a drop-in replacement and print the solder mask as you have it today. So more or less 80% of a board is still green, or we change one step more to only functional surface printing, as shown in this example. All the data conversion can be done in our process data conversion. You can create different height steps in the solder mask, and also you can add graphical elements like a dynamic QR or DMC code to add an identification number to the board, or use it to print logos or watermarks for counterfeit protection, for example. So a very big step here in the area of sustainability, because really you need less resources to make the same functionality of a board. So this sums up the presentation about all the design features where you can impact with our production the environment and save a little bit of resources. So a clear definition of the requirements between the designer and the manufacturer makes sustainable production of the circuit boards, and the best production step is the one that is not needed. Thank you for your audience.